Today we're going to look at linear and quadratic functions in specific. We've been looking at functions for a while now, the idea that a function passes a vertical line test. For every x value, there's one unique y value. Okay, we kind of worked through a lot of different details of functions last chapter. Now we're going to go back and revisit the linear and quadratic functions under the category of functions, as well as this idea of polynomial functions. Linear and quadratic are specific polynomial functions. A function that's a polynomial has a couple key things. First of all, it's set up in this kind of messy looking format. When we actually put in values here, it doesn't look so terrible. Some of the key things that determines if something's a polynomial is first that this n, notice the n's specifically in its exponent form, when the n is in the exponent, it has to be not negative, and it has to be an integer. No fractions. Remember, the fractions give us our radicals. And so we have all these a sub 1, sub 2, sub 3's, all those. Those are the coefficients of x. All this is like something along the lines of 5x to the 8th plus 2x to the 3rd minus 5x, something along that lines. Okay. They say that the coefficients need to be real numbers and that the first one, the leading coefficient, has to not be 0. Okay, if the function's given with all that information, then it is a polynomial function. And then one of the things we talk about in polynomials is their degree. Okay, degree is specifically n, and if we, as we mentioned here, n, one of the ways we see it most clearly is it's the exponent. So the degree is n, which is the, I should add, biggest exponent. Then, that a sub n, remember that's here in front of the first x, if it's written in order with the biggest exponent, next smallest, and working its way down to any constants at the end. The leading coefficient is that first a sub n. It's the coefficient of the term with the biggest exponent. Okay, we want to categorize our polynomial functions. I mentioned that linear and quadratic functions fall underneath the category of polynomials. So first we have a function that's simply f of x equals 0. Okay, this is one of those special ones that has a specific name to it. We call it the 0 function. Okay, what that's saying is for every x value, the function's value is 0. For that, when we have a degree, we have no degree to it. We give it a degree of undefined. Okay? There's no x. It's just 0. Okay? We don't see that one that often, so you don't need to worry about it. It's just interesting to have and to be aware of. It's a good thing to be aware of. The next one is f of x equals 4, f of x equals negative 8, or f of x equals a third, some constant. Okay? That is our constant function. F of x equals a constant, a number of any sort, as long as it's not 0. It can be a decimal, it can be a fraction, it can be positive, it can be negative. There's no x there, and if we have no x, that's the same idea as x to the 0, because remember that an exponent of 0 turns whatever you're working with into 1. So if I have something like 4x to the 0, it's 4 times 1, which is just 4. Okay, so the degree is 0. Remember, degree is the biggest exponent. Then we have anything in the form of ax plus b. My guess is you could name that yourself. That would be a linear function. Okay, its degree is 1. It has an x to the first power. And then our next one, again, you're familiar with this, ax squared plus bx plus c. Hopefully, we can all recognize that that is a quadratic function. And its degree is 2 because the biggest exponent is 2. Okay, that's kind of some of the key things we need to be able to identify about polynomials. Here's a table to let us practice in some more general terms where they're not specifically exactly in this form. One, we have to decide if something's a polynomial. So one of the key things to determine if something's a polynomial is if it fits this information. But let me kind of summarize that and what the key things you have to look for. One of the things is that there are no variables in the denominator. Okay, that comes from the non-negative integer exponents. If I had a negative exponent, that would take this x and move it down to the bottom. Okay, but it's a little hard to see in these words, so one of the things you'd look for is no negatives, or no negative exponents, or no variables in the denominator would be another form we would see that in. When we're looking at the variable, one of the things it needs to be is something, a multiple of the variable to a power, plus or minus another term with a multiple of the variable to a power. There's no other operations. We have no operations besides our basic addition, subtraction. Get that down. Besides the regular old addition, subtraction, multiplication, division, okay, and exponents. Those are okay. All those operations are fine. But if we have things like square roots, absolute values, and maybe cosine or any of those things, those are not polynomials. It needs to be able to be written just like this, though that looks a little hard to read. But all that's saying is some number that's a real number, so maybe 3.8, times x to a non-negative integer power, so x to the 4th or x to the 12th. It has to be integers, so it can't be decimals or fractions. And let's add that again just to make sure we're clear on that. No decimal or fraction exponents. Okay, non-negative, I hope that's clear, but reminder of what integer means as well. So those are the rules we're really looking at as we look at this table down here. We want to decide, is something a polynomial function first? Okay, so I look at this first one. It has 2x to the negative third plus 5. Okay, as we look at that, one of the things we need to notice, and we're really focusing around the variable. Okay, the coefficient is a real number. Looking at the exponent on the variable, is that non-negative integer? Well, we see the negative there, so that breaks that rule. So that is not a polynomial function. Okay, if not, why not? It has a negative exponent. Okay, we can't have negative exponents. That would ultimately put a variable down the denominator, because we'd move that x to the negative third down to the bottom to be x to the positive third. And that doesn't fit our rules of polynomials. Okay, we can't answer the rest of it because, well, it's not a polynomial. Okay, now we're going to go on and look at the next one. We have negative 5 plus x to the negative 5 plus 3x. Okay, looking at that, the coefficient's real. The exponent is a 1, so that's a positive integer. Okay, there's no other operations. Yes, this is a polynomial. Okay, if it's yes, we're supposed to answer what degree it is. Degree talks about what the biggest exponent is on the variable. We look at our x. It has an implied 1. We don't have it written, but that gives us a degree of 1. Okay, and then the leading coefficient is the coefficient of that term with the biggest degree, biggest exponent. So that x's coefficient is 3. Okay, why don't you just for a moment do the top row here. Decide polynomial, 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 yes or no. Okay, pause if you need a little more time. So for the first one, we could think of this as 14x to the 0. That would be fine. Another way to look at that, because x to the 0 is the same thing as 1. So this is a polynomial, yes. Okay, we actually see it above. It's our constant function. It fits under the category of polynomial. And so it is a polynomial, so we want to look at what the degree is. Okay, why don't you fill in what you think the degree is? Okay, it is degree 0. That's what when we wrote out the x to the 0, we can see that. When we have a constant function, we even have it up here, the degree of that function is 0. And then for this it says, now what's the leading coefficient? Well, a coefficient technically needs to be multiplying an x. It's not the constant value. I know we put this x to the 0 there, but that's not really a part of it. That just kind of helps you understand why the degree is 0. So for this, there's none. There is no leading coefficient because there's nothing multiplying an x in the original function. Okay, hopefully you put no for the second one. There's this fourth root that has the x's in it. With that, we do not have a polynomial because we have another operation. It can't be written simply in this form. We have to add the fourth root, and that makes it not a polynomial. So for this, it's not a polynomial because we have the fourth root with x's inside. Okay, so it can't answer anything more. On the last one, hopefully you did say that that was a polynomial. And so the degree is the biggest exponent that we see. So we have an x to the first power and an x squared. So 2 is our degree. And then the leading coefficient has to be on the x. I'm sorry, it has to be with the term with the biggest degree. So that's here in front of the x squared, which is a -2. And then I'm going to add one more here on the side, which I might have to zoom out for, or this is going to get kind of funny. There we go. Let's add one more, because I think it'll be helpful to see it a little bit further. To distinguish with that square root piece, if I have f of x equals square root of 3, okay, notice the square root's ending, times x to the 4th. And you're not seeing that very well. Okay, that's a 4th power. Okay, that, because there's a square roots there, but that's okay. It's on just the coefficient, and the coefficient is a real number. It's the square root of 3. It's not a nice integer by any means, but it's a real number. That is a polynomial function. Okay, and the degree, well, there's an x to the 4th power, so the degree is 4. And the coefficient is the coefficient of that x to the 4th, so it is the square root of 3. Then our last piece we're going to look at for this first video is something we've done many times. It says write an equation for the linear function such that f of -1 is 2 and f of 2 is 3. Okay, we need to interpret that information. What this information tells me, if f of -1 is 2, remember it's f of x. So it tells me when x is -1, the value of f of x is the y is 2. And when f of 2 is 3, it tells me when x is 2, the y value is 3. Okay, why don't you pause the video right now and take a moment and write the equation of the line that goes through these 2 points. And I'm going to go ahead and work through it here now. So first we find our slope. Change in y over change in x. 3 minus 2, 2 minus the -1, we get a slope of 1/3. Okay, then we use our slope and one of the points. Okay, maybe you choose the one that is both positive numbers, so you don't have to worry about the negative. We get y minus 3 equals 1/3 times x minus 2. We distribute, because we want to write this as a function, so we definitely need to solve for y. So we get y minus 3 equals 1/3 x minus 2/3. If I add 3 to both sides, I get my function f of x equals 1/3 x plus 7/3. Okay, there's my linear function that goes through those 2 points. Okay, make sure you watch the next video.